Okay, so just carrying on immediately from the previous video on multiplexing within optical communications. Time division multiplexing we already know about. We just send one signal, bit 1 of signal 1, bit 2 of signal 1 then follows after we send bit 1 of all the other signals first, or however many bits you send at a time. Frequency division multiplexing is where we split them by different frequencies. By using modulators to shift and low pass filters to cut off the high frequencies, and then modulators to shift them to different bands. But the eagle-eyed among you may well have spotted that wavelength division multiplexing seems to be very similar because this is constant. So we are sending our pulses of light down our glass wire, which is very, very thin. We're not changing medium. So the refractive index is constant because it's all in the same medium. So if we increase the wavelength, then we've got to decrease the frequency. Alternatively, if we decrease the wavelength, then we've got to increase the frequency. So effectively, these are the same thing. We call them different just to distinguish between what the input signal, the information signal is. So frequency division multiplexing is referring to an analog signal being used as the information signal, whereas wavelength division is if we have the input signal, the information signal, as a digital signal. That's just a little bit of technical detail that we need to keep an eye on. Okay, we're just going to have a look through a couple of questions. I would encourage you to pause the video at this point and have a go at these two questions. Okay, in this first question, we're given the wave speed, so that's c, and we are given the frequency, and we're asked to work out the wavelength. So you should be thinking c is equal to f lambda. Lambda is therefore equal to the speed over the frequency. So that is 1.8 times 10 to the 8 divided by 120 terahertz. So obviously these values are much higher than what we're used to with digital. So that's 10 to the 12. So that is really, really small, as we expect. High frequency, low wavelength, so 1.5 times 10 to the minus 6, or 1.5 micrometers. Okay, again, I would encourage you to pause the video at this point and have a go at this question, which has two parts. Okay, let's have a look through this question. So we were asked to calculate the bandwidth available between the wavelengths 1300 nanometers and 1350 nanometers and also given the wave speed. So bandwidth, remember, is the range of frequencies in which our cable or whatever it is we're using to send the signal is effective at operating. That's what bandwidth is. It's about a range of frequencies. So we need to convert these into frequencies to do this calculation. So we're using that formula again, c equals f lambda. So in this time, we're going to say that the frequency is equal to the speed over the wavelength. So we've got 2 times 10 to the 8 divided by 1350 times 10 to the minus 9. That's this one here. So that is 1.48 times 10 to the 14 hertz. So that's the top one, and if we look at the bottom now, same idea, frequency is equal to wave speed divided by wavelength. Okay, so those are our two values. Obviously, notice because we're doing 1 over the quantities, this one being the lowest and this one being the highest has switched over. Bandwidth is just the difference between these two values. So the highest frequency, you take away the lowest. So that is, obviously it's quite small, so that's 5.698 times 10 to the 12 hertz, or 5.698 terahertz. Very, very large value. And we're asked to calculate the maximum number of channels that we could get in, and each channel is 160 gigahertz. So this is coming back to this equation to do number of channels. So that's the available bandwidth over the channel bandwidth. So that's just a formula we've already seen when we looked at the first communications chapter. Sorry about that. Sorry about that. I was just trying to zoom in when I didn't want to. So this value we previously counted divided by 160 e to times 10 to the 9. So that would be 35.6. We need to round this down because we cannot have even 0.6 of a channel. We need a whole channel. So it's going to be 35 channels. Now this is obviously a lot higher than the values we saw when we looked at digital communications with copper wire, and the bandwidth is also a lot higher. So that's why everyone wants to do fiber optics. Okay, that's it. Do make sure that you've got all the diagrams and all of the example questions down in your notes.